Now at this point, he had one final goal, to FC it at the legendary 150% speed. Before he went for attempts on that again, he took a break from the song in general and focused on other FCs. Randy would come back to the 150% FC grind with a teaser video on July 18, 2018. The first clip was of him FCing past Bridge 1, while the next clip gave a much stronger glimmer of hope, an FC from Herman solo to the outro. Then, on August 3, 2018, he managed to FC the entire solo 6 times in a row. What made him able to FC everything so consistently now? One of Randy's most missed sections in his 150% runs would be the grace notes before what the that I've mentioned multiple times throughout this video. Normally a player would downstrum all of the strum notes before transitioning to the tapping section, but since this is 150, Randy had to take a different approach. There are 7 strums you have to precisely time and then anchor the very next note right after strumming it in multiple quick successions in order to combo these types of notes. Downstrumming allows a player to facilitate their timing better as compared to alt strumming since they have more control over it. However, the strums were too fast to downstrum all 7 of them, so Randy had to come up with a different solution that would prevent him from falling behind or not being able to transition into the tapping section properly. On the first clip I showed, he came up with a new technique that he would downstrum the first 3 notes, upstrum the next one, and then downstrum the last 3. This allowed him to hit the grace notes much more fluent than before, and within a few weeks, he was able to optimize this technique to the point where this was becoming a relatively consistent section now. Now that we've analyzed the part that was originally giving Randy trouble, and how he was able to overcome it, his journey to FCing the song would be much more challenging, as Randy would face heartbreak unlike any other grind with the song he has had in the past. Just 3 days after his announcement on July 18th, 2018, he would get a -2 run-in where he messed up the strumming transition in twin solo. A few days later, and he missed right after the grace notes in the outro. Lastly, he would have another run in the outro the very next day, and he went as far as to miss in the last 20 notes of the song. Randy was not giving up though, as he had been relentlessly practicing the solo to assure that he would be comfortable enough to FC the song after such a strenuous section. 300 BPM strumming, multiple 30+ notes per second sections, absurdly hard time strumming, and nothing but sheer dedication has led Randy to finally write the last chapter that is now a 150% FC of Through the Fire and Flames expert chart.
Oh, come on. Wow. Okay. What the fuck? Oh my god! First fucking try! Oh my god! Holy shit, man! Oh my god! Holy
Not
crap!
As impressive as Cliffs of Dover.
Boy!
Even after a decade, Guitar Hero 3's Through the Fire and Flames expert chart remains the most iconic chart in Guitar Hero, and its history is nothing short of fascinating when you look at how far players took the song to its absolute physical and mental limits. In 2007, some people thought an FC of the song would not have been possible until last year. If you tried telling people the types of scores done now were even remotely possible at one point, no one would have believed you for a second. This song managed to bring together so many people, and the support was always overwhelming for anyone who wanted to take the song to the next level. It's a mystery what anyone has in store next to achieve on this song. Will Randy FC it blindfolded on 125% speed? Will Darkly come back and display his skills once again on the song? Or will someone else come out of the woodwork with a completely new idea that will shock the community once again? It's only a matter of time at this point. But for now, we should cherish what this song has done for the game and appreciate what the players have done to get it to where it is now. Thank you all so much.
Alright, what's the plan here? Here are the two things I'm going to try and weigh. Is it better to force black to go uncastled and have my pawns split, or to allow black to keep castling open and take the knight? Those are the two things to weigh. Let's keep the structure as is. Let's keep pressure here. Have to be a bit careful. Aw, man. You sneaky guy. You sneaky guy. Wow. A sneak artist. Is this the plan? A3 here? No. Okay, let's stop bishop to b4. Oh! Oh, bishop b4 could still be played. Chop, chop, my queen is hit and my rook is gonna fall. Oh, are they gonna see it? Please no. I could basically resign after bishop b4. Yes, they might have been listening. It's a sneaky tactic, a stream tactic. I have an in-betweener. Got in-betweenered. Were they listening? Were they listening? Oh, it's a stream tactic. Watch out for the stream tactics. Out of nowhere. Woo! They weren't listening, were they? Okay, hang on. Let's focus here. Let's focus. Sneaky, sneaky, sneaky. Oh, were they listening? Were they listening? All right. Alright, what's the plan here? Here are the two things I'm going to try and weigh. Is it better to force black to go uncastled and have my pawns split, Hi everyone, it's Jerry. Let's have a look at a game from the ongoing 2019 Altbox Norway chess tournament. On the white end, Ding Liren, his opponent Wesley So. The format for this tournament is atypical and important to note. In each of the rounds, competitors play one classical time control game, and should the result be decisive, the winner earns 2 points towards the tournament standings, the loser 0, and the round is over. If, on the other hand, the result of the classical game is a draw, each player earns a half point towards the tournament standings, and must play an additional game before the round ends. So, that game is an Armageddon game. That's what I'm about to share with you in this video, the Armageddon game from round 1 between Ding Liren and Wesley So. So how do things work? Well, white has 7 minutes, black has 10. There's an increment of 3 seconds implemented starting at move 61. Black has draw odds, and the winner of this game earns an additional full point towards the tournament standings. One other note, players maintain the same colors as they had in the classical game. So for the mathies out there, if you're keeping track, at the end of each round, you walk away with 0, half, 1.5, or 2 points. Okay. This begins as an English opening, but quickly transposes into a Queen's Gambit declined exchange variation, Black opting to recapture on d5 with the knight, welcoming a minor piece exchange, in the process building White's center, White now with a majority. It's struck at, thematic, and move 7 we have Rook b1, a move that says I'm not welcome to any more minor piece exchanges, at least for now. Most popular on this move 7 is knight f3, which would be welcome to an additional minor piece exchange that we could see in the following way. Bishop b4, and there you go. These two watching from the sidelines. So it's first Rook b1 interfering with Bishop b4 and exerting pressure against the queenside. Only after Bishop e7 do we have Knight f3. Castles, Bishop c4, some prep work by Black for b5, prevented. Queen c7. Without question, this is a familiar position to Ding Liren. One game, he had this position as White against Vladimir Kramnik at the 33rd European Club Cup Open 2017, where he followed with Bishop to d3, and Kramnik eventually put the knight on b4 with tempo. So likely with this idea in mind, White plays Bishop e2 in this game. Seems a bit more cautious, going to e2. Why would I go on this, keep it on this diagonal, and one day stare at h7, more aggressive, right? Well, we're seeing a reason not to maybe go to d3. Okay, b6, castles, takes. Black is fianchettoing, throwing a punch. Only now does the bishop go to d3. And after knight c6, what does White have up his sleeve? How is he going to address the knight b4 move? Without question, this is a key square in this position. It is a hole in White's camp, and it's could always have additional support. A5, knight b4 already has enough support. If Black wants to put a piece there, he's going to put a piece there. White has to find a way to work around a knight on b4. So an instructive moment, for me at least, is this move 15, these next few moves. How to reorganize the pieces on the queen side. We have Rook b3, vacating b1 for the bishop. Now this isn't some, rook lift, some coin flip of a rook lift. You can be sure Ding Liren is not taking out his favorite coin and saying heads, Rook b2, tails, Rook b3. No, Rook b3 also stays out of the bishop's way. Bishop b2 would be a good follow-up should Black apply more pressure to d4. Additionally, Rook b3, this can really turn into a star piece one day. Bishop backs up, knight moves forward, and there you go, rook opposite the king. So there is some nice lateral potential for the white rook on the third rank. Black gives the rook a kick, back, Rook b2. Black returns, and now we have Rook d2. It may seem tempting to go here. Open file, the knight's in the pin, but Black gets out of the pin and says now this would hit that much harder. So it's Rook d2, and when I see this position, I think to myself, boy, there's a lot of energy being built up in the white position. White is really gearing up for a d5 break. The mobility of the white pieces will spring to life. d5 is nearing. There's a thematic pawn break in the center, an important sequence to be familiar with within this structure. First, the black rooks are involved. White is fianchettoing. d5. Here is this pawn break I'm referring to. d5. After knight b4 and bishop b1, of course. Takes. And, of course, we recapture, right? No. We bypass that pawn. Now, this is a pawn sacrifice. What is happening with it? Play d5, and after it takes, you just sneak right by. Well, there are many things to note. For one, when black played rook d8, the rook was on a half-open file. It was staring at white pieces. When the bishop played to b7, what was it doing? It was staring at a white pawn, at one point threatening a white pawn. This is no longer the case. The black pawn, we can say, interferes with the black piece's mobility. Additionally, white has now a
What's going on YouTube? ADC Art Attack here, and welcome back to a brand new drawing video. In today's video, we're going to be doing a speed drawing. Now, this drawing comes in response to a lot of people who have been requesting that I do some speed drawings and that I do some more Dragon Ball stuff. So, that's what we're going to do today. I've been thinking lately, maybe I'll do a speed drawing once every 2 weeks. What do you think about that? I like to mix the so maybe we'll keep the regular content coming, but we'll do a speed drawing every now and then. Let me know your thoughts down below, and of course, let me know what you'd like to see in the future. Now that being said, I'm not going to talk anymore. I'm going to let you enjoy this video. Today we'll be drawing Ultra Instinct Goku performing a Dragon Fist. This is something that I haven't seen anyone do yet, and kind of hoping I'm the first. I highly doubt it, but hey, it would be cool. So stick around, enjoy the drawing video, and I'll see you at the end. speed drawings every now and then. I think they're pretty cool. They just give me time to relax and just draw without the, you know, the stress and the pressure of doing the challenge guides. This drawing was fun to do. And yeah, I really, at the end of this, I was thinking to myself, right, we're going to add some aura to this. And when I did it, I was like, no, because I had to peel off the plasticky cover thing. And I was really upset the way it turned out. However, we saved it at the end. We used some white fine liner or something like that. We used some white gel pen and some colors over it, and we just sort of went around those edges. I think I cleaned them up a little bit quite well, and I think it looks pretty good. I'm really happy with the results, and I do hope
Every year, more than 100 countries send 6 of their brightest teenagers, or the occasional prepubescent prodigy, to represent them at the International Math Olympiad, commonly known as the IMO. Considering that each country has its own elaborate system of contests leading to their choice of 6 representatives, the IMO stands as the culminating symbol for the surprisingly expansive and wonderful world that is contest math. The contest itself is essentially a test, split over 2 days, with 3 questions given over 4.5 hours each day. The questions are all proofs, meaning you don't simply find some numerical answer. You have to discover and articulate a rigorous line of reasoning to answer each difficult question, and then each one is scored on a scale from 0 up to 7. Of interest to you and me today is the one from 2011, with 563 total participants representing 101 countries. I know what you're thinking, and the answer is yes. Those do all happen to be prime numbers. But that's not why this test was interesting. Out of all these prime problem solvers, only one of them, Lisa Sauermann from Germany, got a perfect score. And the only thing standing between the next 2 runners-up that year and a perfect score was problem number 2. And this problem is beautiful. And despite evading many of the world's best mathematicians of their age, the solution is something that anyone watching this video can understand. So, let's begin by reading through it carefully. Let S be a finite set of at least 2 points on the plane. Okay, so as you read the question, it's often helpful to start drawing an example for yourself. Assume that no 3 points of S are collinear. In other words, you never have 3 points lining up. So you can probably predict that the problem's going to involve drawing lines in some way that 3 points on one line would mess things up. A windmill is a process that starts with a line L going through a single point P in S. The line rotates clockwise around the pivot P until the first time that line meets some other point belonging to S. And again, while reading, it's helpful to draw out an example. So we've got this line that's pivoting around some point until it hits another. This point, Q, takes over as the new pivot, and the line now rotates clockwise about Q until it next meets a point of S. This process continues indefinitely. Alright, that's kind of fun. We keep rotating and changing the pivot, and you can see why they call it a windmill process, and you can also see why they specified that no 3 points lie on one line. You wouldn't want to run into the ambiguity where you don't know which pivot to switch to. Okay, so with all this setup, what's the question?
Show that we can choose a point P in S and a line L going through P such that the resulting windmill uses each point of S as a pivot infinitely many times. Alright, depending on your tolerance of puzzles for puzzle's sake, you might wonder, why would anyone care about such a question? There's a very good reason, in fact. I would argue that the act of solving this will make you better at math and related fields, and I'll explain why once you've seen the solution. But certainly on the surface, it feels disconnected from other parts of math. I mean, you look at other Olympiad problems and they often involve some function to analyze or a numerical pattern to deduce, maybe a difficult counting setup or an elaborate geometric construction. But problem 2, it's an unusually pure puzzle. And in some ways, that's its charm. Proving that some initial condition will result in this windmill hitting all the points infinitely many times, well, that doesn't test your knowledge of a particular theorem. It tests if you can find a clever perspective. But that blade cuts both ways. Without resting on an existing result from math, what could possibly prepare someone to study for something like this? And in fact, that brings us to the second unusual thing about this problem. Based on the results, I'm guessing that it turned out to be much harder than the contest organizers expected. You see, typically, the 3 problems each day are supposed to get progressively harder. They're all hard, of course, it's the IMO, but problems 1 and 4, they should be doable. Problems 2 and 5, they're challenging. And problems 3 and 6, well, they can be brutal. But take a look at how many of our 563 participants that year got perfect scores on each of the problems. Only 22 of them got full marks for question number 2. By contrast, 170 got a perfect score on problem 5, which is supposed to be about the same difficulty, and more than twice as many got a perfect score for problem 3, which is supposed to be harder. Some of you might notice that only 6 students got full points for problem 6 that year, so by some measure that was the hardest problem on the test. In fact, the way I introduced things earlier was a little disingenuous. The full data would suggest that problem 6 was the real clincher. But what's strange is that if you look at the results of those 6 students who solved this hardest problem, all of whom are clearly phenomenal, world-class problem solvers, this windmill puzzle evaded 5 out of 6 of them. But again, this problem is not hard because of the background knowledge it demands. It asks only for insight. So how do you approach something like this? The first step with any puzzle is to simply play around with it and get a feel for it. And it's always good to start simple and slowly get more complicated from there. The simplest case would be 2 points, where the line trades off between each point. And that works well enough. Adding a 3rd point, it's pretty clear that the line will just rotate around them. It might not be entirely clear how you would phrase this as a rigorous proof yet, but right now we're just getting a feel for things. The 4th point is where it gets interesting. In some places, your windmill will go around the 4 points just like it did with the triangle. But if we put it inside that triangle, it looks like our windmill never hits it. Looking back at the problem, it's asking you to show that for some starting position of the line, not any position, the process will hit all the points infinitely many times. So for an example like this, if you start with the line going through that troublesome middle point, what happens? And again, at this point, we're just playing around, perhaps moving your pencil among dots that you've drawn on a piece of scratch paper. You want to believe a result before you try too hard to prove it. Here, you'd see that your windmill does indeed bounce off of all of the points as it goes through a cycle, and it ends up back where it started. The worry you might have is that in some large sets of points, where some are kind of inside the others, you might be able to start off on the inside, but maybe something about this windmill process takes the line to the outside, where as time goes on to infinity, it'll be blocked off from those inner points. If you play around, and mind you, it can take some time to draw out many examples and think this through, you would notice that when the line starts off passing through the middle of the points, it tends to stay there. It never seems to venture off to the outside. But can you guarantee that this will always happen? Or rather, can you first make this idea of starting in the middle a little bit more rigorous, and from there prove that all the points will be hit infinitely many times? As a general problem-solving tip, whenever you have a vague idea that feels productive, you should of course find a way to be more exact about what you're saying, but preferably put numbers to it, and then see if you can ask questions about those numbers. In our example, one way to formalize this idea of a middle is to count how many points are on either side of the line. If you give the line some orientation, you can reasonably talk about a left half, say coloring all the points of the left blue, and a right half, say coloring all the points on the right brown. And what it means for a line to be in the middle is that there are as many blue points as there are brown points. For the moment, let's say that the total number of points is an odd number, and the point that the line passes through is colored white, sort of a neutral color. So for example, if there were 11 points, you would have 5 blue ones on the left, 5 brown ones on the right, and the single white point as the pivot. The case with an even number of points will be similar, just slightly less symmetric. What this gives us is a new question to ask. What happens to the number of blue points and brown points as the process plays out? In the example on screen now, you might notice it's always 5 and 5, never changing. Playing around with other examples, you would find that the same is true. Take a moment to pause right now and see if you can think through why exactly that would happen. Why would these numbers not change? Well, the key is to think through what happens as the line changes its pivot. Having given the line an orientation, we can talk reasonably about which half is above the pivot and which one is below. If the line hits a blue point on its left, it must happen below the pivot. So then when it changes the pivot and continues rotating clockwise a bit, that old pivot, now above the new one, ends up to the left, meaning it ends up in the blue region. And entirely symmetrically, when it hits a brown point, it happens above the pivot, meaning that the old pivot ends up in the brown region. So no matter what, the number of points on a given side of the line, that cannot change, except for the instances where the line's passing through 2 points at once. When you lose a blue point, you gain a new one. When you lose a brown point, you gain a new one. And that is our key insight number 1. So why would this imply that the line must hit every point infinitely many times, no matter what weird set of points you could dream up? Well, the second key is to think about letting this process go until the line has turned 180 degrees around. What that means is it's parallel to the starting position, and because it has to remain the case that half the points are on one side and half the points are on the other, it must be passing through the same point it started on. I mean, think about it. If it ended up on some other point, it would change the number on a given side. Additionally, since the line has rotated halfway around, everything that was blue has become brown, and everything which was brown has become blue. And the only way to change a color is if you get hit by the line. So, for our odd-numbered case, that means that after a half rotation, the line is back where it started, and it's hit all of the other points. So as time moves forward, it repeats this exact set of motions over and over, hitting all of those points infinitely many times. For the case with an even number of points, we need to alter the scheme slightly, but only slightly. To make it so that the number of blues can equal the number of browns, let's say that the pivot counts now as a brown point. So to define our initial condition, we still say for a given angle of the line, select an initial point so that half of the points are blue, all on the left, and half of them are brown, now either meaning they're on the right or the pivot. The same argument from before implies that after a 180 degree turn, everything has swapped colors. But this time, the line will be passing through a different point after that first half turn, specifically one that used to be blue. But after another 180 degrees, it has to be passing through the one that it started on. Again, the logic is that it's parallel to its starting position, and if it was passing through any other point, the number of points on a given side would have to be different. So once more, we have a cycle which hits all of the points and which ends in the same position where it started. This time it takes 360 degrees, but that doesn't matter. As the cycle continues, it'll hit all the points infinitely many times. Stepping back, there are two important lessons to take away from this puzzle. The first one social, and the second one mathematical. Once you know this solution, and if you kind of ponder it a bit and turn it around in your head a couple times, it's very easy to fool yourself into thinking that the problem is easier than it is. After all, of course the number of points on a given side stays constant, right? Of course that's a question you would ask. And of course when you start in the middle, every point will switch sides after a half a turn. But the advantage of this problem coming from the IMO is that we don't have to rest on subjective statements. We have the data to show it's a genuinely hard problem, in that it evaded many of the world's best students who are demonstrably able to solve hard problems. In math, it is extremely hard to empathize with what it feels like to not understand something. I was discussing this video with a former coworker of mine from Khan Academy who worked a lot with people creating math exercises, and he pointed out that across a wide variety of contributors, there's one constant. Nobody is able to tell how difficult their exercises are. Knowing when math is hard is way harder than the math itself. This is important to keep in mind when teaching, but it's equally important to keep in mind when being taught. On our windmill puzzle, even if counting the number of points on one side seems obvious in hindsight, you have to ask, given the vast space of possible things you might consider, why would anyone's mind turn to that particular idea? This brings us to the mathematical takeaway. What ultimately led to the solution was finding something about the complex system which stays constant during this chaotic unfolding. This is a ubiquitous theme through math, and especially through physics. We're finding what's called an invariant. Topologists do this when they count the number of holes in a surface. Physicists do this when they define the ideas of energy and momentum, or in special relativity, when they define more abstract ideas like proper time. As a student, it's easy to take for granted the definitions handed down to you. But the more puzzles you solve where the insight involves an invariant, the more you come to appreciate that each one of these definitions was once a clever discovery. Terence Tao, one of the greatest modern mathematicians and the world's youngest IMO medalist, wrote that mathematical problems or puzzles are important to real mathematics, like solving real-life problems, just as fables, stories, and anecdotes are important to the young in understanding real life. Sure, these kinds of puzzles are contrived, but they carry lessons relevant to useful problems you may actually need to solve one day. Maybe it seems silly to liken this windmill puzzle to a fairy tale, a mathematical Aesop summarizing that the moral of the story is to seek quantities which stay constant. But some of you watching this will one day face a problem where finding an invariant reveals a slick solution, and you might even look like a genius for doing so. If a made-up windmill prepares you for a real problem, who cares that it's a fiction? Sometimes math and physics conspire in ways that just feel too good to be true. Let's play a strange sort of mathematical croquet. We're going to have two sliding blocks and a wall. The first block starts by coming in at some velocity from the right, while the second one starts out stationary. Being overly idealistic physicists, taking a quote from Stephen Strogatz, "Since Newton, mankind has come to realize that the laws of physics are always expressed in the language of differential equations. Of course, this language is spoken well beyond the boundaries of physics as well, and being able to speak it and read it adds a new color to how you view the world around you." In the next few videos, I want to give a sort of tour of this topic. The aim is to give a big picture view of what this piece of math is all about, while at the same time being happy to dig into the details of specific examples as they come along. I'll be assuming you know the basics of calculus, like what derivatives and integrals are, and in later videos we'll need some basic linear algebra, but not too much beyond that. Differential equations arise whenever it's easier to describe change than absolute amounts. It's easier to say why population sizes, for example, grow or shrink, than it is to describe why they have the particular values they do at some point in time. It may be easier to describe why your love for someone is changing than why it happens to be where it is now. In physics, more specifically Newtonian mechanics, motion is often described in terms of force, and force determines acceleration, which isn't about change. Equations come in two different flavors: ordinary differential equations, or ODEs, involving functions with a single input, often thought of as time, and partial differential equations, or PDEs, dealing with functions that have inputs. Partial differential equations are something we'll be looking at more closely in the next video. You often think of them as involving a whole continuum of values changing with time, like the temperature at every point of a solid body, or the velocity of a fluid at every point in space. Ordinary differential equations, our focus for now, involve only a finite collection of values changing with time. And it doesn't have to be time per se. Your one independent variable could be something else, but things changing with time are the prototypical and most common example of differential equations. Physics offers a nice playground for us here, with simple examples to start with, and no shortage of intricacy and nuance as we delve deeper. As a nice warm-up, consider the trajectory of something you throw in the air. The force of gravity near the surface of Earth causes things to accelerate downward at 9.8 meters per second per second. Now, unpack what that's really saying. It means if you look at that object free from other forces and record its velocity at every second, these velocity vectors will accrue an additional downward component of 9.8 meters per second every second. We call this constant 9.8 g for gravity. This is enough to give us an example of a differential equation, albeit a relatively simple one. Focus on the y-coordinate as a function of time. Its derivative gives the vertical component of velocity, whose derivative in turn gives the vertical component of acceleration. For compactness, let's write that first derivative as y dot and that second derivative as y double dot. Our equation says that y double dot is equal to negative g, a simple constant. This is one where we can solve by integrating, which is essentially working the question backwards. First, to find velocity, you ask, what function has negative g as a derivative? Well, it's negative g times t, or more specifically, negative gt plus the initial velocity. Notice, there's many functions with this particular derivative, so you have an extra degree of freedom which is determined by an initial condition. Now, what function has this as a derivative? Well, it turns out to be negative 1/2 g times t squared, plus that initial velocity times t, and again, we're free to add an additional constant without changing the derivative, and that constant is determined by whatever the initial position is. And there you go, we just solved a differential equation, figuring out what a function is based on information about its rate of change. Things get more interesting when the forces acting on a body depend on where that body is. For example, studying the motion of planets, stars, and moons, gravity can no longer be considered a constant. Given two bodies, the pole on one of them is in the direction of the other, with a strength inversely proportional to the square of the distance between them. As always, the rate of change of position is velocity, but now the rate of change of velocity, acceleration, is some function of position. So you have this dance between two mutually interacting variables, reminiscent of the dance between the two moving bodies which they describe. This is reflective of the fact that often in differential equations, the puzzles you face involve finding a function whose derivative and/or higher-order derivatives are defined in terms of the function itself. In physics, it's most common to work with second-order differential equations, which means the highest derivative you find in this expression is a second derivative. Higher-order differential equations would be ones involving third derivatives, fourth derivatives, and so on. Puzzles with more intricate clues. The sensation you get when really meditating on one of these equations is one of solving an infinite continuum. Some of you may have seen in school that the surface area of a sphere is 4 pi r squared, a suspiciously suggestive formula given that it's a clean multiple of the more popular pi r squared, the area of a circle with the same radius. But have you ever wondered why this is true? And I don't just mean proving the 4 pi r squared formula, I mean viscerally, feeling to your bones a connection between this surface area and these 4 circles. How lovely would it be if there were some subtle shift in perspective that shows how you could nicely and perfectly fit these 4 circles onto the sphere's surface? Nothing can be quite that simple, since the curvature of a sphere's surface is different from the curvature of a flat plane, which is why trying to fit, say, a piece of paper around the sphere, it just doesn't work. Nevertheless, I would like to show you two separate ways of thinking about the surface area that connect it in a satisfying way to these circles. The first comes from a classic, one of the true gems of geometry that I think all math students should experience, the same way all English students should read at least some Shakespeare. The second line of reasoning is something of my own, which draws a more direct line between the sphere and its shadow. And lastly, I'll share why this fourfold relation is not unique to spheres, but is instead one specific instance of a much more general fact for all convex shapes in 3 dimensions. Starting with the bird's eye view here, the idea for the first approach is to show that the surface area of the sphere is the same as the area of a cylinder with the same radius and the same height as that sphere. Or rather, a cylinder without the top and the bottom, what you might call the label of that cylinder. And once you have that, you can unwrap that label to understand it simply as a rectangle. The width of this rectangle comes from the cylinder's circumference, so it's 2 pi times r. And the height comes from the height of the sphere, which is 2 times the radius. And this already gives us the formula, 4 pi r squared, when we multiply the two. But, in the spirit of mathematical playfulness, it's nice to see how 4 circles with radius r can actually fit into this picture. The idea will be to unwrap each circle into a triangle, without changing its area, and then to fit those nicely into the unfolded cylinder label. More on that in a couple minutes. The more pressing question is, why on earth should the sphere be related to the cylinder in this way? The way I'm animating it is already suggestive of how this might work. The idea is to approximate the area of the sphere with many tiny rectangles covering it, and to show how if you project these rectangles directly outward, as if casting a shadow by little lights positioned on the z-axis, pointing parallel to the xy plane, the projection of each rectangle onto the cylinder, quite surprisingly, ends up having the same area as the original rectangle. But why should that be? Well, there are 2 competing effects at play here. For one of these rectangles, let's call the side along the latitude lines its width, and the side along the longitude lines its height. On the one hand, as the rectangle is projected outward, its width will get scaled up. For rectangles towards the poles, that length is scaled up quite a bit, since they're projected over a longer distance. But for those closer to the equator, the effect might be close to nothing. But on the other hand, because these rectangles are at a slant with respect to the z direction, during this projection, the height of each such rectangle will get scaled down. Think about holding some flat object and looking at its shadow. As you reorient that object, the shadow looks more or less squished for some angles. Now take a look, those rectangles towards the poles are quite slanted this way, so their height is going to get squished down by a lot. For those closer to the equator, oriented somewhere closer to parallel to the z-axis, the effect, it's not as much. It will turn out that these 2 effects of stretching the width and squishing the height cancel each other out perfectly. Already, as a rough sketch, wouldn't you agree that this is a very pretty way of reasoning? Of course, the meat here comes from showing why these 2 competing effects cancel each other out, and in some ways, the details fleshing this out are just as pretty as the zoomed out structure of the full argument. So let's dig in. Let me go ahead and cut away half of the sphere so that we can get a better look. For any mathematical problem solving, it never hurts to start by giving things names. So let's say that the radius of the sphere is r, and for one specific rectangle, let's call the distance between that rectangle and the z-axis d. You could rightfully complain that the distance d is a little ambiguous, depending on which point of that rectangle you're going from. But for tinier and tinier rectangles, that ambiguity will become negligible. And tinier is when this approximation with rectangles gets closer to the true surface area anyway. To choose an arbitrary standard, let's say that d is the distance from the bottom of the rectangle. Now to think about projecting this out to the cylinder, what we're going to do is picture 2 similar triangles. The first one shares its base with the base of the rectangle on the sphere, and has a tip at the same height but on the z-axis, a distance d away. The second triangle is a scaled up version of this, scaled so that it just barely reaches the cylinder, meaning its long side now has a length r. So the ratio of their bases, which is how much our rectangle's width gets stretched out, is r divided by d. What about the height? How precisely does that get scaled down as we project? Again, let's slice a cross-section for a cleaner view. And in fact, why don't we go ahead and completely focus our view to this two-dimensional cross-section. To think about the projection, let's make a little right triangle, like this, where what was the height of our spherical rectangle is the hypotenuse, and the projection is one of the legs. Pro tip, anytime you're doing geometry with circles or spheres, keep in the forefront of your mind that anything tangent to the circle is perpendicular to the radius drawn to that point of tangency. It's crazy just how helpful that one little fact can be for making progress. In our case, once we draw that radial line, together with the distance d, we have another right triangle. And often in geometry, I like to imagine tweaking the parameters of a setup and imagining how the relevant shapes change. This helps to make guesses about what the relations might be. In this case, you might predict that the two triangles I've drawn are similar to each other, since their shapes seem to change in concert with each other. This is indeed true, but as always, don't take my word for it. See if you can justify this for yourself. Again, it never hurts to give more names to things. Maybe let's call this angle alpha, and this other one beta. Since this is a right triangle, we know that alpha plus beta plus 90 degrees must be 180 degrees. Now let's zoom in on our little triangle and see if we can figure out what its angles might be. Notice this 90-degree angle, which comes from the radius being perpendicular to the tangent, and how when it's combined with this beta here and some other little angle, it forms a straight line. So that other little angle must be alpha. And this lets us fill out a few more values, which reveals that this little triangle also has angles alpha, beta, and 90 degrees. So it is indeed similar to the big one. Deep in the weeds like this, it's sometimes easy to forget why we're doing this. Remember, what we want to know is how much the height of the sphere rectangle gets squished down as we project it out. And that's the ratio of this little hypotenuse to the leg on the right side. By the similarity with the big triangle, the ratio of those two sides is, again, r divided by d. So indeed, as this rectangle gets projected outward, the effect of stretching out the width is perfectly cancelled out by how much that height is getting squished due to the slant. As a fun side note, you might notice that it looks like the projected rectangle is a 90-degree rotation of the original. This would not at all be true in general, but by a lovely coincidence, the way I'm parameterizing the sphere results in rectangles where the ratio of the width to the height starts as d to r. So, for this very specific case, rescaling the width by r over d and rescaling the height by d over r actually does have the effect of a 90-degree rotation. And this lends itself to a rather bizarre way to animate the relation, where instead of projecting each rectangular piece as if casting a shadow, you can rotate each one of them 90 degrees and then rearrange them all to make the cylinder. Now, if you're really thinking critically, you might still not be satisfied that this shows us what the surface area of the sphere is, because all of these little rectangles only approximate the relevant areas. Well, the idea is that this approximation gets closer and closer to the true value for finer and finer coverings. And since for any specific covering, the sphere rectangles have the same area as the cylinder rectangles, whatever value each of these two series of approximations are approaching must actually be the same. I mean, as you get really aggressively philosophical about what we even mean by surface area, these sorts of rectangular approximations are not just aids in our problem-solving toolbox. They end up serving as a way to rigorously define the idea in the context of smooth, curved surfaces. This kind of reasoning is essentially calculus, just without any of the jargon. In fact, I think neat geometric arguments like this, which require no background in calculus to understand, can serve as a great way to tee things up for new calculus students so that they have the core ideas already in their head before seeing the definitions which make them precise, rather than going the other way around. Alright, so as I said before, if you're the kind of person who's just itching to see a direct connection to these four circles, one nice way to do that is to unwrap those circles into triangles. If this is something you haven't seen before, I go into much more detail about why this works in the first video of the calculus series. The basic idea is to relate thin concentric rings of the circle with horizontal slices of this triangle. Because the circumference of each such ring increases linearly in proportion to the radius, always 2 pi times that radius, when you unwrap them all and line them up like this, their ends will form a straight line, as opposed to some other curved shape, which gives us a triangle with base 2 pi r and height r. And 4 of these unwrapped circles fit perfectly into our rectangle, which is in some sense an unwrapped version of the sphere's surface. Now that's pretty satisfying. But you might nevertheless be wondering if there's some way to relate this sphere directly to a circle with the same radius, rather than going through this intermediary of a cylinder. I do have a proof for you to this effect, leveraging a little trigonometry, though I have to admit I still think the comparison to the cylinder wins out on raw elegance. Now I'm a big believer that the best way to really learn math is to do problems for yourself, which is a bit hypocritical coming from a channel essentially consisting of lectures. So I'm going to try something a little different here, and present the proof as a heavily guided sequence of exercises. Yes, I know that's less fun, and it means you have to pull out some paper to do a little work, but I guarantee you will get more out of it this way. At a high level, the approach will be to cut the sphere into many thin rings parallel to the xy plane, and to compare the area of these rings to the area of their shadows on the xy plane. All of the shadows of the rings from, say, the northern hemisphere make up a circle with the same radius as the sphere, right? Well, the main idea will be to show a correspondence between these ring shadows and every second ring on the sphere. Challenge mode here is to pause now and see if you can predict how that comparison might go. Let's label each one of these rings based on the angle theta between a line from the sphere's center to that ring and the z-axis. So theta ranges from 0 at the North Pole all the way up to 180 degrees at the South Pole, which is to say from 0 to pi radians. And let's call the change in the angle from one ring to the next d theta, which means the thickness of those rings will be the radius, r, times d theta. Alright, structured exercise time. We'll ease in with a warm-up. Question number 1. What is the circumference of this ring, say at the inner edge, in terms of r and theta? Once you have that, go ahead and multiply the answer by the thickness, r times d theta, to get an approximation for the ring's area.